The purpose of this lab is to find the coefficient of kinetic friction between the block and the table. For the first part, we focus on the mass and the block as a system. So here's our hanging mass, and here's our block. The block is sliding across the table, and the distance the block slides across the table is equal to the height that the hanging mass travels before it hits the ground. So from that, we gather that h is equal to h. These two distances are the same. And in our diagram, we decided to use energy to solve the problem. So red represents the before energy, and blue represents the after energy.
The reference point of potential energy that we're using here is gravitational potential energy equals 0 here. So that's why we can say that as soon as it hits the ground, there's no gravitational potential energy. Next, what we're going to do is look at the mass of the block and the sample mass of this hanging mass as a system. So here we're pretending that there's no bend right now. We're kind of just like lifting these two up. So here we know that here's the mass of the block, and there's the force of friction acting in this direction. And here is the sample mass, which the force of friction is the gravitational force is acting in this direction. So our before statements and our after statements. Before statements: the kinetic energy of the block is 0 at the beginning because it's not moving, and the gravitational potential energy of the hanging mass is mass of the sample plus times gravity, 9.8, times the height at which it is elevated from our reference point. So there is potential energy right over here in the before picture of the sample mass. The kinetic energy of the sample mass is 0 because, again, it's not moving. After. Now, here, once the block starts moving, right before it stops, due to the force of friction acting on its already presumed inertia, the kinetic energy is 1/2 mass of the block times velocity squared. As we said before, the velocity is going to be equal because not only is the time equal, but the height that each moves is equal as well. We know that the potential energy of the hanging mass over here, because of our reference point, is 0. And we know that the kinetic energy of the sample mass right before it hits the ground is equal to 1/2 mass of the sample mass times velocity squared, which, as we know, is equal to the velocity over here. Now, here's a really quick free body diagram of our, this is supposed to be a B, our mass of the block. So here the force of friction, the normal force is acting upwards, the force of gravity is acting downwards, and the force of friction is acting here. Our sign convention is up and to the right, therefore the angle between the two forces here is 180 degrees, something that we're going to need for this portion of the lab.
We have the work of the non-conserving force, which in this case is friction, and it's the change in energies, the final energy minus the initial energy. And here we just used a bunch of algebra, and we solved for velocity squared, which we will use in part 2. Okay, so this is the same diagram from the first part, where we're showing the blocks before they're moving and after, and this is the displacement of the block that's on top of the table after the hanging mass has hit the ground. Because of inertia, the block continues to move until friction is acting upon it.
Again, we want to make clear that the height in both here and here is the same, and the time based on experiments is also the same. Thus, the velocity that we solved for in part 1 is going to be the same for both blocks. So now, going back to this equation, to this diagram, first we found the sigma y statement, so the force is in the y direction, and we drew a free body diagram over here. So for the mass of the block, we can see that there's a normal force acting upwards, the gravitational force is acting downwards, and the force of kinetic friction acting in this direction. As we used in the first diagram, our sign convention is up and to the right. Again, once you write your sigma y statements, you can solve for the normal force, and this will be used in further problem solving. Over here, we know that before the energy of the initial is equal to just the kinetic energy, which is 1/2 mass of the block times v squared, which we solved for in part 1, and after the kinetic energy is 0. So the work done by the non-conserving force, which is friction, is equal to delta E, which is equal to the first, the final energy, which is 0, minus the initial energy, which is 1/2 m sub v v squared. So then, with some further algebra,
this is our equation from before with work non-conserved equals change in energy. So now we're simplifying algebraically. So we get to the point where the force of friction is equal to mu k Fn, and we substituted Fn with mbg. So the mass of the block times the force of gravity. So when we solve for mu k, we said that v squared, or it's equal to v squared over 2g delta x, because the mass of the blocks cancel out. So this is where we substitute in our previous formula for v squared, which is 2 times negative mu k, mass of the block times gh, plus mass of the sample mass times gh, all over the mass of the block plus the mass of the sample mass. We substituted that into our formula for mu k. Then we simplified it out to get each of the terms that contain mu k on the left side. We factored those terms out, and we were left with the equation mu k equals the mass of the sample mass times the height, divided by quantity of the block mass and the sample mass times the distance traveled by the sliding block, plus the mass of the block times the height. Then we used our measured variables, which were the height that the sample mass fell and was 0.5 meters. The distance the sliding block traveled after the sample mass hit the floor was 0.17 meters. The mass of the block was 0.286 kilograms, and the mass of the sample mass was 0.200 kilograms. And once we plugged all that in, we got a coefficient of friction equal to 0.443.